this is all very new. I spent a lot of time over the last couple of weeks when I thought I should be writing my slides, trying to debug a load of problems so I could do some benchmarks. But, you know, it's fresh. So I'm going to talk about, first of all, what PyViennaCL is. Then I'm going to talk about how it comes to be useful in Python and how PyViennaCL integrates the two kinds of things, and then what happens next. So my motto for PyViennaCL is basically making scientific computing really kind of easy. Because there's all this hardware around, GPUs. I have 2 in my laptop, but it's actually quite difficult to do parallel programming. And if you're doing computation, if you're doing calculations, you shouldn't really have to care about how to get the best performance. You should just want to do your calculations. And so that's what I've been trying to make easy. But PyViennaCL is a C++ library, and it does primarily 4 things. It's a set of kernel templates in OpenCL, in CUDA, and also you can run on the CPU. And they're templates because they're tuned to your hardware according to what kind of device you have. It's also a generator that does that tuning, and according to the kernels you want to use, the shapes of your objects, and the hardware you're using. And it's a scheduler, and that does things like managing memory buffers and dispatching the kernels that you want to do. And finally, there's a C++ API, and it's like Boost if you use Boost. But that's, you know, not Python. So it's developed by a group in Vienna, but I just come to it through the Google Summer Code, and I'm quite new myself. I'm just, barely finished my undergraduate work. But it's, got a liberal license. You can do what you want with it, basically. And its mathematical features are all very familiar. You can do scalars, vectors, and matrices. It's not n-dimensional like Numpy, but you've got a lot of useful stuff. Dense, sparse matrices. You can do the standard kind of operations on your matrices and vectors, additions, products. You can solve systems iteratively or directly. We've got a couple of algorithms there. There's a couple of other things like eigenvalue computations and Fourier transforms and matrix decompositions. But what PyViennaCL can do is let's see how it does it. And that brings me on to this kind of portable performance idea. PyViennaCL is hardware agnostic. Its backend looks at what you're doing and how you could do it and dispatches it to the hardware you've got. We can do it on the CPU using OpenMP. We can do it on whatever OpenCL hardware you've got, and if your hardware is in the database, you'll get the best performance you can. And it can do it on CUDA, and later on we'll be able to do heterogeneous and distributed computing as well. The problem I had was that C++ isn't Python, and actually PyViennaCL's API uses expression templates, and that defines the expressions in terms of types. But when you've got Python, which does its dynamic typing at runtime, it's quite difficult to encode that. So we have another API, which isn't the API you would use if you use it in C++, and that's just producing a graph of your mathematical expression and using the scheduler to dispatch that. And that brings with it a load of quite cool features. So we can eliminate temporary objects, and we can fuse kernels, and so we can maximize the amount of time spent doing computation rather than waiting for your computation, your CPU, your GPU, or your memory access. And I'll talk about that in a minute. So consider these couple of operations. It doesn't really matter what X, Y, Z, and U are, but just think of the structure of the operations. So we could do these. We could do y and z and then multiply it by alpha and then substitute that into this expression for u. But that would produce all this unneeded data. Why would we compute y and z twice? And we'd access the memory for those more than we need to, and it's a lot of duplication. So if we represent these as a tree, which is what computationally we do in PyViennaCL, we can see we've got these common features. And so the generator the kernel generator in PyViennaCL can look at, or will at least, we'll see, can look at this kind of tree and notice the shared features and fuse the kernel so that we only do what we have to. And the result of that is that we can minimize the storage and access and the kind of computation time that we need to do what we want to do. That's a bit of an abstract example, and we can't quite do that yet, but we can do a couple of things. We can do things like, on the right-hand side here, if you've got two expressions like this, the kernel generator can look and see what you're doing, and combine both of those instructions into a single operation, tune it to your device, doesn't form a temporary for these two operations, and reads them only once. And there's a similar situation on the left-hand side. You get one kernel, one operation, so there's only one load of execution overhead. You only need to read the operand once rather than 4 times if you're doing it naively, and again you get the kind of device-specific kernel. There are a lot of the operations. There's a lot of scope for parameters that you might have to tune, and we've got a bit of magic to get the kind of optimized device-specific kernels that we need. We have a bit of guesswork, and we're working on getting minimizing the size of the parameter space to get the best kind of kernels. And we've got some benchmarks that show we're on the right track. We're doing quite well. But in Python, at the moment, for instance, if I'm using Ubuntu on this computer, and if I install Numpy and SciPy, I get the kind of the reference version of the linear algebra subroutines, and they're not very fast. I mean, they work, but they're not very fast. And even if I, as I've done, install an optimized version, I just get a CPU version. And that's fine in a lot of cases. If I'm working with matrix systems up to a few hundred unknowns, then that's probably all I need. But when you've got large systems, that's not the best thing, and you have to start thinking about what you can do. And there are a couple of things out there. There's thiano, which I don't know very much about, and that's probably more along the same lines as what PyViennaCL does. And cuDamat and Numpy, which are quite thin wrappers over the kind of cuBLAS stuff, and are only limited. They're limited to only NVIDIA hardware. So what if you've got a GPU that isn't NVIDIA, or what if you have more than one device you want to use? And I had a lot of trouble. I didn't succeed trying to get Numpy to look at 2 NVIDIA GPUs. It's quite difficult to tell it what to do, but we have no problem like that. Of course, you can write the code yourself in OpenCL or CUDA or C, but then you get into the territory of thinking more about the optimizing the algorithms and implementing those quickly than actually getting your work done. So I got a couple of quotations from the Zen of Python. Simple is better than complex. Complex is better than complicated. And whilst under the surface, PyViennaCL and PyViennaCL are quite complex, they get out of the way and they do the complicated stuff for you. So your life can be made simple. And like a good Zen koan, you can be both. So I want to talk a bit about how PyViennaCL works, and then I'll get to what it looks like in your code and talk about the performance and benchmarks. So you've got a thin layer over a boost Python wrapper, and I know at the moment there's a lot of press about Python, and that's got C++ support recently, but there was a tutorial, I think, which I missed, about boost Python, and I've got a lot of time for that. I think it's quite elegant, and it works quite well for my case, because with this template API, there are float matrices, double matrices, all various kinds of integer matrices, and there's a lot of stuff to get over, so I just use C preprocessor macros and get it all out the way like that. But to translate the kind of PyViennaCL graph into Python, we've got a couple of things. There's the node class, the leaf class, which is anything that holds data like a matrix or vector. There's the node class, which I think of as anything that does the computation, and there's the statement which works in the background to do the dispatching. And the thing is, it doesn't really matter what the actual classes are for a user. You should just be able to use them to do what you want to do. And that works. So if we look again at the example I showed earlier, I replaced the plus symbols with the classes I use in PyViennaCL. And if you type u equals x plus y plus z into Python using PyViennaCL objects for x, y, and z, then u isn't a matrix or a vector depending on what x, y, and z are. You get an add class, but you don't need to think about that. You can treat it like a vector. And then when you use it outside of PyViennaCL, if you want to get access to the result of that computation, all the stuff happens in the background. So PyViennaCL produces this statement object, which deduces the type and the shape of the object needed to hold the result of the computation. It then creates an assign node, which is another technicality in PyViennaCL, so that it knows where to store the result. It schedules the computation on whatever hardware you're using, points the result attribute of the object U at the computed result, and then uses that result in any computation or whatever you're doing afterwards. So you don't need to think about that. You can just use it as you would like an array object in Numpy. So here's some Numpy code, and it's probably very familiar, and it's not very interesting. It doesn't really matter, but I'm just using it as an example. It's quite straightforward, but the point I'd like to make is that doing the high-performance stuff doesn't need to be much more complicated. The only thing, apart from stuff we do in Numpy, constructing and the operands and doing the computation, the only other thing we need to do really is tell PyViennaCL that we've got a matrix and a vector, for instance. Then we can use the syntax like we do in Numpy. We've got the dot attribute, or unfortunately I chose to use a star as the matrix product operator before the whole matmal stuff of PET 465 and using the @ symbol in Python 3.5 to represent matrix multiplication. But I'm sure I can sort that out. But for now, it's like the Numpy matrix class more than anything else. And then, as I said, if you do something like, I don't know, print is a simple one, that in the background enqueues the operation on your compute device and then stores the result in the memory of your host. So as I said, I tried to, like with the WCS axes talk in here before this, I tried to keep it familiar. So it's like Numpy. You've got a similar D-type interface, and you can use D-type objects from Numpy to describe the kinds of data in your matrices, like 32-bit single precision floats or double precision floats. We've got similar kinds of constructors, and you can as in the example, you can just construct PyViennaCL objects from Numpy ones anyway. And then there are similar attributes and function calls. So you've got a .t for matrix transposition. The dot product method is the same. And the solver interface is fairly similar to the one in SciPy. And as I mentioned, of course, the star is probably the wrong choice. Also, like in Numpy, we want to minimize copying. And so if you take a range or a slice of a matrix, then you don't get another object. You get a proxy view of the original object. And you can mix and match the Numpy and PyViennaCL types in your operations. I don't recommend that because I think explicit is better than implicit. But if you do, PyViennaCL will be quite conservative, and will try and convert it in a way that looks plausible. And you can compare across different types. Of course, there's all this technology, but it doesn't really matter if it doesn't amount to very much. But I've managed to get some benchmarks, and they do seem to work quite well. And I'd like to make the point again, it doesn't matter what your hardware is, and we've got decent performance on AMD, NVIDIA hardware, and on the CPU, though I don't have CPU benchmarks here. So here's a benchmark for vector addition. As we can see, we've got fairly close to peak performance, and in vector addition it's memory bound, so it's not. It depends on the memory bandwidth of the device rather than the compute performance. But here we get close. We get to that peak performance, the peak bandwidth here, and in fact we've got lower overhead than CUDA, and so we get an extra 5 gigabytes per second better bandwidth. Of course, it's much better than doing it on your CPU. And there's a similar picture in the matrix vector vector product that is also similarly memory bound. I'm not sure what happened to Numpy with CUDA there. It seemed to be, for some reason, doing it on the CPU. I'm not sure, but in any case, don't worry, because you can use PyViennaCL. And of course, there's the sort of matrix product, and we get depending on this is a fairly new result, so there are a couple of anomalies where the padding or the various parameters we use to represent the matrix on the device they're not quite right, but the point is that we get fairly close to the peak kind of performance on whatever kinds of hardware you're using. But if there's an operation that you want to do, or you want to play with an algorithm of your own that's not in PyViennaCL, then you can, and you can interoperate with OpenCL just as you can with Numpy, and we're working on CUDA support at the moment. And you can even write a class that will integrate with the expression graph, and then will inherit all the useful features like the delayed execution of that. So I've got a couple of simple examples. So supposing v, w, and x are vector instances, then we can write some OpenCL code here, and it's very simple. We just point to the buffer of the vector objects and then enqueue the kernel on our own, and it will do the operation on the device we've chosen for our context. And if we can, here we've got a similar kind of thing. So here we've got this is a custom node, and it inherits from that kind of node class, which tells PyViennaCL that it's a mathematical operation, that it should be dispatched. And so we've got a bit more boilerplate here. We need to tell PyViennaCL what the operation, what operands the custom node can work on, and we need to tell it what the results are going to be of those operations, and we need to, of course, provide the source of the compute kernel we want to use. And this is the example here I've given uses OpenCL, but we can write a function that uses CUDA, and we could also do it. We could just provide a normal Python function and do it in host memory or whatever. I've left out a bit here. Really, we should also provide a function so that PyViennaCL can deduce the sizes and shapes. So if we're doing matrices, for instance, we need to be able to deduce the size and shape of the result from the operands if we can, but here I've left that out. Also, if we're doing OpenCL, then we should probably provide the work group sizes so the hardware knows how to operate. And then, given that, we can just represent our own custom node, and we can use it like any other object in PyViennaCL, and it will know what to do according to what you've told it. There are a couple of things missing from PyViennaCL that are in PyViennaCL, but there's not very much, and it's fairly functional as it is. We're missing QR factorization, the Fourier transforms, preconditions, and structured matrices, but I'm working on those, and they'll be done in the next couple of weeks. CUDA support is rudimentary right now, but given that we've got the OpenCL support, and it's all quite agnostic at the moment, that's coming. But if you've got an NVIDIA device, you can just use the NVIDIA OpenCL right now. Of course, there's always more optimization to do. But the main thing that's missing are users. And we've got all this technology and not very many people to use it. I've had a number of inquiries and some bug reports, but I don't think I'd be surprised if there were 20 users. There should be more, and I think we've got something quite good here, and I'd like to see more people using it. So try PyViennaCL. It's very easy to install, although as in the talk preceding this one, the code I've been talking about here is on GitHub, and it's fairly experimental, but we're supposed to have a new version out fairly soon. And of course, suggestions and bug reports. It's hard to know what's good and what's bad if there aren't any users, so it would be good to hear from people, and of course you can just talk to me. And that's all I've got to say for now. So thanks.
So